Assalamualaikum everyone. My name is Ahmad Faris Daniel bin Zaini, and I'm honored to present to you one of Japan's most iconic engineering fact, the Tokyo Gate Bridge. This stunning structure not only enhanced the landscape of Tokyo Bay but also served a vital piece of infrastructure connecting key areas of the city. So, before we dive into detail of the Tokyo Bridge itself, I would like to introduce my team. First, we have Abang Izrul. Second, we have Muhammad Azamuddin. The third, Nur Fatiha. And number four is Nur Ain Amelie. Me and my team will be discuss about architectural design and structural features of the bridge.
So today our group members will present about introduction, literature review, problem definition, mathematical modeling, result discussion, and conclusion.
Introduction. Structure analysis in static is a key process in engineering, determining how structure respond to applied load while maintaining equilibrium, ensuring safety and optimizing material use for efficient, cost-effective design of infrastructure.
Now I will present about the literature review. So, the Tokyo Gate Bridge is a cantilever bridge located in Tokyo, Japan. It opened on February 12, 2012 with a total length of 792 meters and a main span of 140 meters. The estimated cost for stage, including the bridge, ranged from 113 billion yen to 119.12 billion yen by 2019. It is known for its efficient truss design and use of high-performance steel, SBHS steel. Trusses are structural system made of two force members arranged in triangular patterns to ensure stability and distribute loads efficiently. In trusses, forces are typically applied at joints and the members experience either tension or compression. Trusses have pin joints and straight members, making them simpler yet highly efficient in load distribution. The Warren Truss, patented in 1946 by engineers James Warren and Willoughby Manzoni, features alternating equilateral triangles. This design evenly distributes loads and resists external pressures, making it ideal for long spans under moderated loads. The Pratt truss is characterized by diagonal members sloping outwards from bottom to the top chord, contrasting with the inward slope of Howe truss. It supports longer spans and heavier loads due to its efficient design, which equally distributes forces across vertical diagonal elements. So in summary, Warren trusses offer simplicity for shorter spans and lighter loads, while Pratt trusses excel under greater loads and longer spans, providing enhanced stability. The Tokyo Gate Bridge leveraged the strengths of both design to meet its structural requirements. Given Tokyo's seismic activity and frequent typhoons, the bridge incorporates advanced engineering features. Seismic isolation devices like base isolators and dampers help absorb and disperse earthquake energy. Aerodynamic design and wind tunnel testing ensure stability during strong typhoon gusts. To analyze the force acting on the bridge, use static equilibrium equations. Total Fx equal to 0, total Fy equal to 0, and total moment equal to 0. For example, in a simply supported beam with applied loads, reactions can be calculated using these principles. Free body diagrams are crucial in visualizing forces and reactions in structural analysis. Both Warren and Pratt Truss play essential roles in modern bridge engineering. The Tokyo Bridge showcases their combined effectiveness in creating a robust and efficient structure. Environmental challenges are addressed through innovative design, ensuring the bridge remains a vital part of Tokyo's infrastructure. Thank you.
Okay, so today I'm excited to present one of the most remarkable engineering facts of modern infrastructure, the Tokyo Gate Bridge. As you can see, the problem definition of Tokyo Gate Bridge is located the area systemically active zone which earthquake, particularly the site of break. In a coastal area with exposure to seawater required of corrosion-resistant material. So, one of the most innovative design solution that we used to help meet this demand was the integration of both Warren and Pratt truss system. So, the system played a crucial role ensuring proper load distribution while allowing the bridge to adapt to the force generated by earthquake activity. So, as we know, the combination of this advanced truss design and material address the complex and challenge of balancing strength and flexibility.
Assalamualaikum warahmatullahi wabarakatuh. My name is Noran Amali Beza Abdul Hadi. My match number is CD240271. So today I would like to talk about mathematical modeling. Mathematically modeling. When analyzing force in a truss, two primary methods can be used, like a method of joint and the method of section. The method of joint involves symmetrically calculation force at every point in the truss by apply equilibrium of equation sum fx equals 0 and sum fy equals 0 to ensure the system is stable. While accurate, the method can be time consuming, especially for large truss, since it requires solving for all force one joint at a time. The method of section is, however, simplify the process by selecting a specific section on the truss by cutting the truss into two parts and focusing only on the section of interest. This method enables the calculation of select member force using equilibrium of equation sum fx equals 0, sum fy equals 0, and sum moment equals 0 without having to solve for every member in the truss. In the analysis, the group choose the method of section to determine the specific force, including force at E1 F2, E2 F1, and E2 F2. So at the first, they calculate the reaction at the support like pin and roller by using the moment equilibrium of equation sum m equals 0 about a point A to find force at the B1, and then use the force equilibrium of equation sum fy equals 0 to solve for force at A1. So once the reaction were determined, the group applied the method of section by making a cut through the truss to insulate the relevant members. So using the moment equilibrium of equation at the F1, so they can calculate the force members at the E2 F2 while additional equilibrium equation were used to determine the force in F3 F1 and F2 F1 and FE1 F1. So this approach allowed for an efficiency analysis of specific force without requiring detailed calculations for every joint and member in the truss. So this is FPD, Fribourg diagram, about explanation and mathematically modeling.
Assalamualaikum. My name is Nur Fatihah bin Sajjad. My number matric is CD240168. So next I will explain about the result. We need to find force in members E1, F1, E2, F1 and E2, F2. Also state whether the member is in compression or tension. Tension is always pulling on the joint, and the compression members are always pushing on the joint. So I choose the method of section because I want to determine the specific members of the truss. So we have 4 steps to solve the problem. The first one is draw the free body diagram of the truss bridge with all dimensions. We need to define the support reaction, whether the pin support or roller support. At the point A, we have a pin support, so AX and AY. So another support at point B is roller support. So its normal force we put as a By. Next, do equation of equilibrium. In this equation, I use total moment Fx and Fy equal to 0. So I calculate the moment at the point A and I assume moment counterclockwise will be positive. So I got the force at By equal to 233.38 kN and the condition of the truss in tension. After that, I use total Fx equal to 0. So this equation only have one unknown. So we know force Ax will be 0. Next, I use equation of total moment at total Fy and we find Ay equal to 216.62 kN in condition tension. For the second step, cut through members of the truss. So I choose a section that easy to us to calculate the force members of the truss. For this diagram, I cut through members E1, F1, E2, F1 and E2, F2, focusing on the left side of the truss. And information, do not cut through members more than 3 members. Why we cannot do that? Because we only have 3 equations and the limit of us to have unknown force is 3, 2. Third step is draw a free body diagram of the section side with the dimension. I guess all 3 members are in tension. For force members are not aligned with the x-axis or y-axis, we need to calculate the base, height, and length of the force. Force at E2 F1, base is 16.67 meter and height is 17.07 meter. Length is 23.86 meter. Same step for the force members E2 F2. So the base is 16.67 meters, height 1.71 meter, and the length is 16.76 meter. For the last step is apply equation of equilibrium to find force E1 F1, E2 F1 and E2 F2. So I use total moment at point F1. So I got force for E2 F2 equal to 684.01 kN in condition tension at Fy next. So I got force for E2 F1 is equal to negative 65.50 kN in condition compression, and the final equation is Fx equal to 0. So force for E1 F1 equal to negative 634.57 kN in condition compression. Next, I will present the discussion of the Tokyo Gate Bridge truss structure. Using the section method, I calculate the external loads, support reaction, and internal force in the truss members. This method highlights how the truss system efficiently transfers loads from the bridge deck to the support, ensuring stability and balance. The support reaction shows a symmetrical load distribution due to the bridge design. At the point A, the pin support handles both vertical and horizontal force, while at point B, the roller support resists only vertical force. This reflects the bridge consideration of structural limitation and environmental impact. The truss design minimizes bending moments by evenly distributing loads among its members, ensuring structural efficiency. However, members under high compression or tension may require additional reinforcement for long-term durability. In summary, this analysis shows the importance of precise calculation and thoughtful design in creating stable and efficient bridge structures like the Tokyo Gate Bridge.
For conclusion, the Tokyo Gate Bridge showcased the power of truss design, incorporating both Warren and Pratt truss elements for efficiency and stability. Warren truss is simple and effective for moderate span, while the Pratt truss optimizes material uses and load distribution, making it ideal for longer spans. The combination of both truss in the bridge design balance ease of construction with efficient load-bearing capacity, reflecting careful consideration of span length, load requirement, and aesthetics. This approach highlights the importance of understanding the truss principle in modern bridge engineering, creating structures that are both efficient and capable of handling modern transportation needs.